all, let's see, I'm sorry for this one day. See, this scheduling has been a little bit of a problem, okay, because we fixed this schedule of this after I had made several commitments. I will talk about it, but anyway, let's first begin the lecture. So we are looking at orthonormal sets. And let me just recall whatever we had. So we had inner product space, so I'll write it as IPS. So we have an inner product space, and we say that a subset of X is orthonormal if the two conditions, any two vectors there are orthogonal for every xy in S, x not equal to y, and any vector has length 1. That is the standard definition of an inner product of an orthonormal set. So then the important thing that we had was the following. One was we first looked at finite orthonormal sets. So if S is a finite orthonormal, I will not write these brackets now, is a finite orthonormal set, then we had the following. A, suppose you look at the subspace spanned by these vectors, LS is the subspace spanned by these vectors, which is the collection of all vectors of the form alpha 1 phi 1 plus alpha n phi n, where alpha j belong to field. If F is, if it's a real inner product space, F is R. If it's a complex inner product space, F is C. So look at that space. For convenience, I will call it W from now on instead of writing it again and again LS. Look at the subspace. Here is the whole space, and here is the subspace. Now, if we take any vector, there is a best approximation of X from among the vectors of W. Okay, so then this is what we had last time. Then for every X, in X, the vector, I will call it as Wx. I don't know what notation I use. J equal to 1 to n, x phi j approximates. Okay, let me first is such that 1 Wx is in W. That thing lies here, and then now if you took the error between x and Wx, that is the smallest, it is less than the error of approximating x by W for any W not equal to Wx in W. If we take any other vector in W, the distance will be more. So Wx is the closest vector to x that is lying in W. So this is the best approximation, and this is the first one we observed, and the second one we observed was that the summation norm j equal to 1 to n mod x phi j squared is less than or equal to norm x squared for every x in X. Okay. These are the two things that we observed, and then using this we extended it to a sequence of orthonormal vectors. So the next thing that we observed was that 2, so we use this to show that if S is equal to phi 1, phi 2, phi n, etc., is an orthonormal sequence, then truncate it at n. If we truncate it at n, for that n this inequality will be true, because for any finite thing that inequality is true. So for every n this will be finite, dominated by this. So the partial sums of the series are bounded above. It is monotone, non-decreasing, because everything is non-negative. So it will converge. Okay, is it then by B we have summation j equal to 1 to n mod x pi j squared is less than or equal to norm x squared for every n. So, they have for any x, this is true for every n, and therefore, the series j equal n equal to 1 to infinity x pi j squared converges and the sum is less than or equal to norm x squared. That is the fundamental thing. This is called the Bessel's inequality. This is the Bessel's inequality when you have an infinite sequence. This is the Bessel's inequality when you have a finite set of orthonormal vectors. So, for every orthonormal set, we have the Bessel's inequality. So, this is all we had. Okay. So, this is where I stopped the lecture last time. Now, we will proceed from here. The question is, will this Bessel's inequality become equality? Suppose mod x pi squared is equal to norm x squared. For example, in the case of 3 dimensions, if we take the 3 I j k vectors and then you take the 3 components x dot I, x dot j and x dot k, and then sum of the components squared will give you precisely the length squared. Now, therefore, when will that happen here? So, the question when can we say that the Bessel's inequality becomes an identity, becomes an equality, okay, let me put it this way, for every x. That is, must be exactly equal to norm x squared for every x in x. So, that is the question. Where does this happen? Let me, of course, I will use these things later. So, let us first say, suppose this becomes an equality, what happens? Suppose this becomes a equality. Okay. So, suppose summation mod x pi j squared j equal to 1 to infinity is equal to norm x squared for every x in x. Then, if a vector is orthogonal to all these phi's, then x pi j will be 0 for all j, and therefore, the left hand side will become 0, and therefore, the right hand side will be 0, therefore, x will be the 0 vector. That means, the only vector which can be orthogonal to all the phi j's is the 0 vector. So, now, then x belongs to x is such that x pi j equal to 0 for every j implies x pi j squared equal to 0 for every j, which implies summation j equal to 1 to infinity x pi j squared is 0, which implies, because this is equal to norm x squared is equal to 0, which implies x is the 0 vector. Of course, the converse is obvious. If x is the 0 vector, this is true. If this is true, by this must be true. If this is true, this must be true. If this is true, this must be true. So, x is then, we can put both ways. They are all completely reversible truths. So, this is the only vector which can become orthogonal to all these vectors is the 0 vector. That is when, if this has to happen, this must be determined. So, okay. So, therefore, we say that Bessel's inequality becomes equality if and only if x phi j equal to 0 for all j implies x equal to 0. So, this is the condition that we require for the Bessel's inequality to become an equality, and this is what we call as a definition that the orthonormal set is complete, which is no more is required sort of thing. So, or we call it an orthonormal basis. If this condition is satisfied, we say it is an orthonormal basis. So, we give a definition. So, an orthonormal set, now I am not assuming whether that set is a sequence or not, it could be even an uncountable set. An orthonormal set S in an inner product space X is said to be a complete orthonormal set or an orthonormal basis if x phi n, x phi equal to 0 for every phi in S implies x is the theta vector. The moment a vector is orthogonal to all of them, then the vector is forced to be the 0 vector. Then we say it is an orthonormal basis or a complete orthonormal set. You will see why we are going to call it a basis shortly. So, how can we write this then? The Bessel's inequality becomes an equality if and only if this phi 1, phi 2, phi n etc. is an orthonormal basis. So, therefore, we have this small result. This result can be written as an orthonormal set. So, let phi n equal to 1 to infinity orthonormal sequence. Then for this the Bessel's inequality becomes equality if and only if this is an orthonormal basis. Or in words, n equal to 1 in symbols, mod x phi j squared is equal to norm x squared for every x in x, if and only if phi 1, phi 2, phi n etc. is an orthonormal basis. That is symbolically can write it like that. So, in that case, that is called, that identity equality is called the Parseval's identity. Okay. This is all generalization of what Fourier got with Parseval's identity, Bessel's inequality, etc. in his classical Fourier analysis. Okay. Now, what Fourier missed was to see give a proof of the fact that the phi 1, phi 2, phi n that he had e to the I n t, the exponentials, actually is a complete orthonormal basis. He assumed and then pursued. He never gave a proof of it, and that to get a proof of it, it took a long time. Okay. We will look at some of those questions again. Okay. Right. So, now we have this, that the Bessel's inequality becomes Parseval's identity if and only if we have a orthonormal basis. So, this is then called Parseval's identity. Now, we will see one more interesting consequence of this. Okay. Now, suppose I have vector x in x, okay. Then I look at the vector x n This is precisely the approximation of x by the first n eigenvectors. So, take the first, I am sorry, I am talking about eigenvectors. The first n vectors in the orthonormal basis, look at that subspace and look at the best approximation of x from that subspace, and this is precisely that vector xn. So, xn is the best approximation of x from the space spanned by the first n vectors in that orthonormal set. Okay. Suppose I have this, suppose I have an orthonormal set, a sequence, and I look at the first n vectors and then look at the best approximation in that. Then let us see, we know that this is the best approximation and therefore this error will give the minimum error. What is that minimum error? Let us calculate that. Okay. That is the least square error. Okay. The error is least and we want to calculate the square. So, this is the least square error. Okay. All least square error computations are essentially like this. So, we calculate the least square error. It's the norm of the square of the norm of the difference vector, but the square of the norm always of any vector is the vector inner producted with itself. So, it is just x minus xn, the inner product. Then the inner product is distributive. There are 4 terms. We can take all the 4 terms. It is x comma x minus minus. So, it is plus xn comma xn minus xn comma x minus x comma xn. Then you will calculate all this now. This is norm x squared. This will be summation j equal to 1 to n mod x phi j squared. This will be again the same. This will be again the same. Okay, using the orthonormality, just take the cross products are all gone. So, only the j terms will remain. So, basically it boils down to norm x squared minus summation j equal to 1 to n mod x phi j squared. Right? So, that is the least square error of approximating x from the subspace spanned by the first n orthonormal vectors. Now, suppose this is true. Suppose if one of them is true, the other one is also true. Suppose we had an orthonormal basis, then we have this equal, this one converges to this as n goes to infinity, and therefore that error will go to 0 as n goes to infinity. That means that the left hand side goes to 0 as n goes to infinity. That means xn converges to x. That means x can be written as the infinite series. Okay. So, what does this say? If phi 1, phi 2, phi n etc. is an orthonormal basis, then by result 1, did I call it result or result 1? By result 1, the RHS tends to 0 as n tends to infinity. Therefore, norm x minus xn tends to 0 as n tends to infinity. Therefore, xn converges to x. Hence, the partial sums of the series converge to x means, and therefore, x can be written as summation n equal to 1 to infinity x phi j phi n. This is precisely what we do when you have a orthonormal. If you have a basis, how do you expand a vector? Simply take the components along each direction and multiply, and calculating the components along each direction becomes easy when you have an orthonormal set, because you have to just take the projection along that direction. Okay, so this is called the Fourier series, the generalized Fourier series of the function x, of the vector x with respect to the orthonormal basis phi. Okay. So, what does that say? Okay. So, we have got conclusion. Phi 1, phi 2, etc. phi n is an orthonormal basis for x, implies every x in x can be expanded as x equal to n equal to 1 to infinity x phi n, and this is called the Fourier series expansion of x with respect to this orthonormal basis. So, with respect to every orthonormal basis, we have a Fourier series. What Fourier actually had done was chosen a very specific basis and expanded everything in terms of. So, he had just shown the way, he just showed the way for us to look at the orthonormal expansions. That such as we did for ijk vectors in 3 dimensions, there is a natural way of doing these things in infinite dimensional spaces. The moment you choose an orthonormal basis, you automatically have a corresponding expansion. So, ijk is nothing special. You could have simply rotated the whole system by 45 degrees and you still have an orthonormal basis and you still have the same type of expansion. Okay. Now, look at reverse. Suppose I had that this fact that everybody could be expanded in Fourier series. Suppose I had the fact that everybody could be expanded in a Fourier series. Okay. Then what happens? If somebody is orthogonal to all of them, then his Fourier series tells he must be 0 vector and therefore it must be a basis. So, if it is a basis, we have Fourier series for everybody. Conversely, if we have a Fourier series for everybody, then that must be a basis. Okay, so conversely, suppose every x can be expanded in a Fourier series, x is equal to summation n equal to 1 to infinity x phi n. Suppose we can do this, then x phi n equal to 0 for every n implies x is equal to theta x, and which implies hence phi 1, phi 2, phi n etc. must be an orthonormal, because that is definition for an orthonormal basis. The definition for orthonormal basis is when somebody is orthogonal to all of them, he must be 0. That is the definition of an orthonormal basis. So, that is implied. So, we can put a if and only if there, and therefore, now this if and only if this if and only if that. So, all these statements are equivalent. So, putting all these things together, the result, now we have bigger result, phi 1, phi 2, phi n etc. orthonormal basis 1, this statement norm x squared is equal to summation n equal to 1 to infinity mod x phi squared for every x in x, and the third statement x is equal to summation n equal to 1 to infinity x phi j are all equivalent. One of them holds, the other one holds. So, saying something is a basis Orthonormal basis is the same thing as saying that every vector can be expanded in that Fourier series. That is the same thing as saying that the norm can be captured by looking at the components along this direction. So, all are equivalent statement, which makes us feel comfortable, because that is what we are all comfortable in n dimensions and linear algebra, and that thing carry over for this situation even when you have an infinite sequence of orthonormal vectors. So, this is then called, as I already said, Parseval's identity. So, if you have an orthonormal basis, you automatically have Parseval's identity and you have Fourier series. Okay. Now, we make it a little bit more general. Now, suppose now let me call now one, let us say 3. Suppose 3 is true. It is easier to start with it. I could have started with any one of them. Now, since they are all equivalent, I will start with the one that is easier. Suppose 3 is true, that is, every vector x can be expanded in a Fourier series. Then take any two vectors x and y in x. Suppose I take two vectors x and y in x, then by 3 x can be expanded in a Fourier series, y can be expanded in a Fourier series. So, the moment I am given that every vector can be expanded in a Fourier series, I expand x in a Fourier series, I expand y in a Fourier series, then what is the inner product between x and y? I have to take the inner product of this and this. Now, all the cross terms will go away because they are orthonormal, and therefore, only the diagonal terms will be there, and the diagonal terms phi n is 1, and only thing is this to this. Now, this is the second factor, so it will come with a conjugate. So, this will be summation n equal to 1 to infinity x phi n y phi n bar. And this is exactly what we had as inner product in our normal. If you have the coordinates, two vectors, to take the dot product, you take the coordinates to the first fellow, multiply by the conjugate of the coordinates to the other fellow, take the sum, and that is exactly what is happening in this situation. Okay, x phi. So, this happens in the most general situation with any complete or any orthonormal basis. Okay, for every x and y. So, therefore, this is called the Plancherel's theorem. Okay, this is the so called Plancherel's. Any Fourier series situation, you will have Plancherel's theorem, you will have Parseval's identity, you will have the Fourier series, and once you start with a orthonormal basis. Okay. So, therefore, we have 3 implies x y is equal to summation n equal to 1 to infinity x phi n y phi n bar for every x y in x. This is called the Plancherel's. I do not know why one is called a theorem and the other called identity. This should have also been called as Plancherel's identity, but it is called Plancherel's theorem. Now, on the other hand, if this holds, then automatically this holds. Why? I can put y equal to x, I get this. So, this implies 2 by taking x equal to y. If I take x equal to y, I simply get mod x phi n squared there, but 2 implies 3. So, all these fellows are equivalent, nothing. So, you can put the same notion of basis in many languages. So, now we have the fourth statement. x comma y is equal to summation 1 to infinity x phi n y phi n bar for every x y in x is also equivalent, to the above. So, the fact that I have a basis, orthonormal basis, can be expressed in many ways. One way to express is that the only vector orthogonal to all of them is the 0 vector. The other way to express it is that the length squared is the sum of the components squared. The other one is that every vector can be expanded in terms of it in the usual manner, and the other one is that the dot products can be obtained through the components. All these one way or the other, or if you have one of them, you can use all of them. That is one thing. If you had gotten one of them, it means that you have all of them under your disposal. So, this is basically the general idea of Fourier series. If you have an orthonormal set, if it is a basis, then you have the Fourier series, you have the Parseval's identity, you have the Planck-Charles formula. Okay. But at no time I am assured you that if you give me an inner product space, there will be a sequence like this which will form an orthonormal basis, or that question. We are saying if that is happening, then all this will happen. But are we talking in mid-air or what is it? Suppose if you may have a complicated situation where there is no sequence which is a basis. An orthonormal set may be very big. We saw one example last time. You take an uncountable set, and then we saw how the L2 space looks in that, and we took a function which takes 1 at a point and 0 at all other points, and the set is uncountable. There are uncountable number of them, they are all orthonormal, and I have an uncountable orthonormal set. So, I am in a deep trouble at that stage. So, what happens in that situation? We will end up in exactly the same situation as the so called L2 space we looked at. That is why we looked at it. So, now I am going to look at, so we saw first finite orthonormal set, then we saw an infinite sequence of orthonormal sets. Now, we are going to look at an uncountable orthonormal set. Okay, so, now I will go back to Bessel's inequality again. Okay. First Bessel's inequality, recall this again. If S equal to phi 1, phi 2, phi n is a finite orthonormal set in X, then norm x phi j squared summation j equal to 1 to n is less than or equal to norm x squared. The fundamental Bessel's inequality, which all started the whole process started because of this. We had this inequality, from this we pushed it to infinity, and then we got all the results. Now, suppose we had this fundamental thing again. Let us go back to this fundamental thing. Now, let us say S is an uncountable orthonormal set, like the one we saw with those functions. Okay. Now, suppose I have an uncountable orthonormal set, then what happens? Now, since that set, say an uncountable set, I can pick finite number of them out of it arbitrarily, pick any finite number of them. Okay. So, but anyway, first of all, what I will do is the following. I will look at a phi from S and look at the value x phi. Okay. Now, that phi may have some information about x or may have no information about x. It has no information about x means there is no component in that direction at all. So, x phi will be 0. So, if I want to study a vector, I am interested only in those directions in which there is some information. So, I want to look at whether this is 0 or not 0, and my interest for any vector will be only on those phi's for which this is not 0, and this we will call it as Sx. It is like support of x from S. Only those places I have some information about x, others do not support any information about x. Okay. So, given an orthonormal set S, uncountable, and given an x, then for that x in that set S, there are only certain fellows who are of importance, others are irrelevant and redundant for this vector x. So, this support of x is what we are going to look at. Now, if x phi is not 0, this set is the same as saying mod x phi is not 0. If the mod x phi is not 0, automatically x phi is not 0. So, we look at it that way. So, it is a real mod, because mod x phi is a real number, it is much easier to look at. So, we are looking at numbers, certain numbers which are strictly positive. So, if mod is positive, so it has to be not 0, that means I want to look at all that x phi greater than 0, because it is modulus. So, it can be either 0 or greater than 0. I do not want 0, so it is greater than 0. So, I am going to look at all the phi's for which this mod x phi is not 0. Right. So, let me now see one trick. Suppose I want to find, I will first find all those fellows. See, I want to find numbers which are to the right of 0, right. I will first find all those who are to the right of 1, right, and then I will find all those who are to the right of half. Then I will find all those who are to the right of 1/3, and then put them together. I would have found all those who are greater than 0, because if somebody is greater than 0, he must be greater than 1 over n for some n. Okay. So, now I will write this in a clever manner. Okay. So, this set Sx can be written as Snx union n equal to 1 to infinity, where Snx is the set of all phi's such that mod x phi is greater than 1 over n. Okay. Why is this true? If somebody is on the right hand side, then he is in one of the Sn's. If he is in one of the Sn, this must be greater than 1 over n for some n, that means it must be greater than 0, and therefore he is on the left hand side. If he is on the left hand side, is greater than 0, therefore it must be greater than 1 over n for some n. So, he must be in one of the Sn's, and therefore is in the union. So, this is a typical way of writing. Very sometimes we look, you are writing things which is greater than 0 in a very complicated manner, but this is what makes things easier. Okay. So, now what I am going to do is, I am going to look at each one of these Sn's. How big Sn can be? So, for each n, how big this set Sn can be? So, now we have the following. I do not know how big it is. Suppose there are 100 fellows in it. Suppose there are 200 fellows in it. I do not know how many fellows are there. Okay. Suppose phi 1, phi 2, phi n all belong to Snx. Suppose these are all in Snx. What does that mean? x phi 1 modulus is greater than 1 by n, x phi 2 is greater than 1 over n, and so therefore, this implies mod x phi j is greater than 1 over n for every j equal to 1, 2 up to n. Now, therefore, summation j equal to 1 to n mod x phi j squared, each term is greater than 1 over n squared, because each modulus is greater than 1 over n. So, each term is greater than 1 over n squared. How many terms are there? N. So, this is greater than n by n squared. Okay? But what can I say about this? Result 1 says, once you have a finite set, that thing can never be greater than normal. So, this is therefore by 1, I will call this as a fundamental. So, by 1, norm x squared is greater than or equal to this, and this is greater than n by n squared. So, what does that say? N has to be less than x squared times norm x squared times this thing. Okay. Now, once the vector x is given for that x, and once I have fixed the integer n, this number is fixed, and n is an integer, capital N is an integer, number of these fellows. So, the total number of fellows cannot exceed this number, and given any positive number, there are only a finite number of integers to the left of it. So, n has to be finite, therefore, n is finite. Oh, so none of these fellows can be infinite, none of these S n x can be infinite. So, there is only a finite number of fellows who are in each one of them. Okay. So, therefore, for example, you already have a fact that you are going to put a threshold level for the coordinates, and if you say 10 to the power of minus 4, beyond that the coordinates can be thought of as 0, there are only a finite number of them. So, the whole problem takes into a compression level, only those coordinates you have to look at. Okay. So, that is one way, that is the fundamental idea of compressions. Fix the threshold level and take only those. Okay. Okay, therefore, each Sn, okay, n is finite, that is what I had written here, and therefore, each Snx is finite. So, therefore, what can I say about Sx? If I put a sequence of finite set, it will be either finite or countably infinite. So, therefore, Sx, the cardinality of Sx has to be less than or equal to f naught. Hence, no matter the fact that S may be an infinite set, S may be an uncountably infinite set. So, you may have an uncountably infinite orthonormal set. However, when it comes to looking at a particular vector, only a countable number of them make sense. Others are all having switch off. For every vector x, there are only a countably infinite number of them which switch on, the rest of them are switched off. But who switches on for whom will depend on which vector you are talking about. That is the difference. Okay. So, hence, for each x in x, there is at most a countably infinite orthonormal vectors, phi 1 which may depend on x, phi 2 which will depend on x, and so on in S, such that x phi j x is not equal to 0, and x phi x is equal to 0 for every other phi in S. That is the beauty of it. So, basically what it says is, you are very comfortable when they have finite orthonormal set. From that we moved on and found out Fourier series, Parseval's identity, Plancherel's formula, etc. and we were comfortable if the orthonormal set was countably infinite. Now what we have is, even if the set orthonormal set is uncountably infinite set, when you are focusing on individual vectors, you are still comfortable, because only countably infinite number of them are relevant, all others are irrelevant. For each vector x, you are comfortable. Previously, you are overall comfortable. Now, for every vector x, we find a comfortable zone, namely these vectors. So, therefore, once we have this, we have all the other things. Then we have one, S is an orthonormal basis. 2, norm x squared is, now for which phi this makes sense? Only those phi's which are in Sx. Now that is only a countable number, and therefore this is a genuine series. It is not a very uncountable sum. It is still a finite countable sum only, and therefore it is an infinite series. And 3, Fourier series summation x phi belonging to Sx. 4, this is for every x, and then x comma y is equal to summation phi belonging to Sx intersection Sy of x phi into y phi bar for every x1. So, we have all are equivalent as before. The theorem about Fourier series is now slightly modified. We have to look at Sx. So, this is called again Parseval's identity. This is called the Fourier series now, and this is called the Plancherel's formula. So, we have the situation whether we have the moment you have an orthonormal basis, whether the basis is finite or countably infinite or uncountably infinite, all these things are valid. We have Fourier series, we have Parseval's identity, we have Plancherel's formula. Okay? Right. Now, what does this all amount to? This all amounts to saying, okay, I will come to this question a little later. So, we will have this for the moment. So, now that is the fundamental thing that we learnt. If there is a basis, if there is an orthonormal basis, then everything is okay. Whatever we do intuitively is valid. We can expand, we can take the components, we can take the length, we can take the inner product to their components, everything is allowed, okay, once you have a basis. But who said that there is such a basis? That is still not the question. So, therefore, whether it is finite orthonormal basis or whether it is countably infinite orthonormal basis, whether it is an uncountably infinite orthonormal basis, once I have it, all these things are comfortable. But how do I know I have them? Okay, so, the question is, how do we know that any given inner product space must have an orthonormal basis? This question is similar to the question that we ask in linear algebra. How do we know that a vector space has a basis? There we do not talk about orthonormal anything, there is no orthogonality, there is no inner product. We have only vector space, we have the notion of linear independence, we have the notion of basis as a maximal linear independent set. Okay. So, therefore, the same question is asked now in the language of orthonormal basis. and whatever we did there, we do it exactly here to get the answer. What did we do there? In the linear algebra, we interpreted basis as a maximal linearly independent set and applied Zorn's lemma to show that it will have to have a maximal linearly independent set. Here we will interpret an orthonormal basis as a maximal orthonormal set, and we will apply Zorn's lemma to show that there is a maximal orthonormal set. Okay. So, let me write that this is similar to the question prime. How do we know that a vector space has a basis? You see? So, approach to Q prime. How do you approach to Q prime? Interpret basis as maximal linearly independent set. Use Zorn's lemma to show existence of maximal linearly independent and therefore a basis. That is the maximal linear independence basis. Therefore, use Zorn's lemma, show the existence of maximal linear independent, and you are done. So, therefore, same approach. Same approach. Okay. Step 1, we will see this is step 1, this is the step 2. We will first see the step 1. Okay. Step 1, interpret orthonormal basis as maximal orthonormal set. What do we mean by this? It is an orthonormal set. We have added it is a set. For that we added an adjective or normal, namely that the lengths have been normalized to 1. For that we added another adjective called ortho, namely that the vectors have been made to be orthogonal. Now we are adding one more, that namely maximal. That set is maximal. What do we mean by this? Okay. So, a set, an orthonormal set S is said to be maximal orthonormal set, said to be a maximal orthonormal set if, first of all, it must be an orthonormal set. If S, okay, we already said if it is already given to us orthonormal set. So, what is the question about maximal? That means nobody can be bigger than him and still be a orthonormal set. That is, if S1 is an orthonormal set and S is contained in S1, then S1 must be equal to S. Nobody can be bigger and contain him. If he contains him, he better be equal. That is all. Other way of saying is that if S1 is any orthonormal set, okay, this is a better way of saying, okay. If S1 is an orthonormal set and if he is bigger than him, the only way is that he better be equal. This cannot be taking place. Okay. No other orthonormal set can contain this fellow properly, okay, or this cannot be a proper subset of any other orthonormal set. So, there are various ways of saying that is S cannot be the proper subset of any other orthonormal set. Okay, that is what is meant by maximal orthonormal set. Now, we look at a basis. Okay. Suppose S is a basis, suppose S is an orthonormal basis. We want to claim it is maximal orthonormal set, and suppose it is not maximal orthonormal set. Then what will happen? It will be a proper subset of some other orthonormal set. Okay. Then S is strictly contained in S1, where S1 is an orthonormal set, because it is not maximal. So, we have started with an orthonormal basis. Suppose S is an orthonormal basis and we want to claim it is maximal. Suppose it is not maximal, then it will be definitely embedded in another bigger orthonormal set, and therefore, we will have S here and S1 bigger, and there must be at least one fellow in that annulus, because it is a bigger set. So, therefore, there exists X belonging to S1 and S, and because S1 is an orthonormal set, norm X will be equal to 1, because the bigger set S1 is also an orthonormal set. Because it is an orthonormal set, every vector there will be equal, having length 1. Now, therefore, X cannot be the 0 vector, because it has length 1. On the other hand, X is orthogonal to all the vectors in S. Why? S1 is an orthonormal set, so therefore, any two vectors in S1 must be orthogonal. X is here and other S's are all there, they are distinct vectors, so they must be orthogonal. But if a vector is orthogonal to all the vectors in a basis, that vector must be 0 vector, because S is a basis. On the one hand, I have X is not equal to theta X, on the other hand, I have X is equal to theta X, a contradiction. And therefore, it must be maximum. So, therefore, S orthonormal basis implies S is maximum. Now, reverse the argument. Suppose S is maximal. We want to show S is orthonormal basis, and so let S be orthonormal, and suppose S is not orthonormal basis. So, since it is not an orthonormal basis, somebody must be orthogonal to all of them without being the 0 vector. So, therefore, there exists a vector not equal to the 0 vector such that x phi is equal to 0 for every phi in S, because it is not a basis. And if that is so, we can call psi as x by norm x, then length of psi is 1. I can divide by the length of x because psi is x is non-zero vector. So, now if you take S union psi as S1, what can I say about this set? Any two fellows here are orthogonal, because it is maximal orthonormal set, any two fellows here are orthogonal, anybody across are orthogonal, because x is orthogonal to all the fellows here, and therefore psi is orthogonal to all the fellows here. Everybody here is orthogonal, everybody across is orthogonal, so it's an orthogonal set, and everybody has length 1. Everybody in S has length 1, psi has length 1, so it becomes an orthonormal set. Which implies S is not maximal orthonormal, because S is now a proper subset of another orthonormal. Something bigger than S is also an orthonormal set, which contradicts our hypothesis. We started with a contradiction. So therefore we have this, if and only if. So now that basis has been interpreted as a maximal orthonormal set. That is the first step, okay, of our proof to show that an orthonormal basis exists. We have shown that a basis, orthonormal basis, can be interpreted as an maximal orthonormal set. Next is to apply the Zorn's lemma to show such a thing exists. Okay. One comment before I conclude is in finite dimensional spaces, we showed that if you take any two bases, they have the same number of vectors. Any two bases will have the same number of vectors, and we called it the dimension of the space. But now when we come to infinite dimensional spaces like this, we have one orthonormal basis and we have another orthonormal basis. Both will have the, when we are talking about infinite sets, we do not talk about number, we talk about cardinality. They both will have the same cardinality. If one is finite, all orthonormal bases will be finite and all of them will have the same number. If one of them is infinite, all orthonormal bases will be infinite and all of them will be equivalent sets. And if one of them is countably infinite, all orthonormal bases will be countably infinite and will have the same number. If one of the bases is uncountably infinite and has the cardinality of the real numbers, then all of them will be uncountably infinite, will have the same real number cardinality. So depending on what sized orthonormal basis we have, the structure of the Hilbert spaces or the inner product spaces change. So what I will do next time is use Zorn's lemma, show the existence of this orthonormal basis, and then we will see, because of the Fourier series, we see the connection between any Hilbert space and the L2 spaces that we had include over the finite the counting measure over an arbitrary set. So the orthonormal basis gives us how to identify any Hilbert space with a proper L2 space, and therefore there is only one type of Hilbert spaces, namely the L2 spaces, and all theorems boil down to L2 spaces. And if the basis is countably infinite, we have what is known as a separable Hilbert space, and if the basis is uncountable, we have non-separable Hilbert spaces. There are two types, separable Hilbert spaces and non-separable Hilbert spaces. In separable Hilbert spaces, we will have the usual Fourier series and all. In non-separable Hilbert spaces, for every x, we are comfortable, we will get a countable set for which it is not zero. Okay. Now before I go again, I have a problem with this Monday. I have to attend a meeting in Trivandrum, whatever it is called now, Thiruvananthapuram. And so with the only other possible date I have for next week is Thursday. Friday, of course, we will have our usual class. Is it possible to meet on Thursday? Are you all free on Thursday evenings? Okay. Thursday. So room has to be found. So, can you check for the room? Thursday, what time? 4 o'clock, 5 o'clock? Phone ilvalle? Idya? Oh, your bookings are here, is it? Okay. See whether there's Thursday anything is there. Thursday is 14th. No, yeah, 14th.